So, why is the fresh water so blue? In fact, this question is related to it's the same question. It's why is the sky blue? It is because the water molecules do not absorb the blue wave, the lights of the blue wave spectrum. As we know, the sun generates a wide array of spectrum, of wavelengths, and that wavelength consists of all kinds of colors. We're familiar with the 7 visible colors, but there really is a spectrum of colors, and it goes all the way to the invisible ultraviolet and infrared spectrums. In those spectrums, we don't see them, but we do see the visible spectrum, which is a very narrow spectrum of light that the eye can see. Let me pass these people first.
Okay, let's look at our example.
Excuse me. So what makes the water molecule blue? Well, strictly speaking, the water molecules are not blue. They, like I said, they only reflect the blue wavelengths. But then the next question is, what caused the water molecules to reflect blue wavelengths? That is related to the energy level of the electrons, of the oxygen and hydrogen electrons, as they bind 2 hydrogens to a single oxygen atom. So that energy level is fixed. Hello. Fixed, and it just turns out at this particular combination of atoms, the blue wave, roughly the blue wave is reflected. So if we really look at the sun's visible light waves, we know the visible light wave is very narrow window of visible wavelengths. But those wavelengths, if you really look into details, there is the so-called Fraunhofer lines. In the late 19th century, German physicists discovered that the visible light waves are actually discrete light waves. And these discrete light waves are due to the quantum energy levels later. Excuse me. Hi. Later discovered by Max Planck, Einstein, and other physicists who basically described that the energy levels of the electrons must be at certain discrete levels, not continuous. Because if they are continuous, there is this so-called blue wave catastrophe. It's kind of hard to describe, but basically it means that if it is continuous wavelengths, then there will be infinite energy in the visible universe, which is not the case. Back to the color of the water wave, and the same goes with the sky. The sky is blue because the oxygens and the water molecule, I think primarily is the oxygen, I could be wrong, that pass through that, because it does not absorb the blue wave, pass through or reflect or whatever. And this is what we see. But to broaden this discussion a little bit, we know the visible lights of the solar spectrum is a very narrow spectrum. To our humans, we see a very narrow window of visible light. Most of the light spectrum is outside our visibility. In fact, we cannot see infrared. We can only feel the heat. we cannot see ultraviolet. We could only feel the sunburn. And that is vast majority of the light energy besides the visible light. And between humans and other creatures and animals, our window of visibility is also slightly different. As we know, dogs and cats and bees and other animals have different visibility. Butterflies and bees, they in fact, some of them are monochrome. In other words, they can only see brightness. Some of them see ultraviolet. I think it was the bees can see ultraviolet or something. But humans can only see a very narrow spectrum. So, round up this discussion, are we talking about chemical properties or are we talking about physical properties? Clearly, we're talking about physical properties. When we deal with the water molecule H2O, it's a chemical compound. But reality-wise, at the bottom of all chemical properties is actually physical property. So chemistry is basically a macro level summary of properties of underlying physical properties. Go ahead. So if we think about Mendeleev, he is the greatest chemistry scientist in chemistry, or you can call it a chemist. But realistically or strictly speaking, Mendeleev is a physicist because he describes the elements in terms of their composition in atoms, in neutrons and protons, and in the atom weight. That's really physics. So the founder of chemistry, I wouldn't call Mendeleev as founder of chemistry, but he is the most important figure in modern chemistry because of the periodic table that he discovered. He is strictly a physicist. So chemist is what started this science, because some of the greatest chemists are those, typically those who discovered certain chemical properties before there is a thorough understanding of the underlying atoms and quantum levels and electrons and atoms and neutrons and protons and so forth. But they have made important discoveries in the chemical properties. There are so many names, but anyway, who discovered the chemical elements, oxygen, carbon, and also the conservation of mass during the chemical reaction. All of that. In fact, one of them I mentioned in the French Revolution is I forgot his French name. He was eventually got his head chopped off because he was a tax collector, and during the French Revolution, they thought he was the enemy of the people. But he was actually one of the monumental figure in discovering that the total mass throughout a chemical reaction does not change. But actually, with the Einstein's general relativity and special relativity, we know that is no longer strictly true, because chemical reaction can release certain amount of energy, and that energy is in the minuscule amount of mass lost. But back in the 18th century, that amount of losses could be considered negligible. That loss is E equals mc squared, that formula. But if we go to the high school chemistry, high school physics, we all have this conservation of energy principle. That is the conservation of energy or conservation of mass or conservation of energy. This is more of a conservation of mass. Mass does not disappear. But with Einstein's formula, with Einstein's law of energy and mass, we know that there's a relationship between the two. Long story short, water molecules we see here, they are from the melting ice. That melting ice came from that glacier, which probably were from the snow a few hundred years ago or a few thousand years ago, because the snow on the top is the fresh snow from last year, but the melting ice most likely is from the snow further down in the glacier, in the ice portion, with a tremendous pressure and grinding against the rocks, they become liquefied and become glacial water. So this water came from the snow a few hundred years ago, or even a few thousand years ago. But what about the water molecule? How old are the molecules? These molecules are probably billions of years old, since the very beginning of the birth of the Earth as a planet. Billions of years old. And they're just being recirculated from water to ice to vapor, back to water to ice to vapor, and just keep on recirculating. So every one of these water molecules, maybe a few hundred years ago, as snowfall dropping onto the mountaintops right here. But before that, it may be as cloud, water vapor in the cloud that came from somewhere else in the Earth atmosphere. And so strictly speaking, these water molecules may even come from another continent, from Africa, from Europe, from Asia, or from wherever. Even more interestingly, there is a probability that this molecule could be part of someone in the ancient times, part of their body's circulation. In other words, as the water they drank, and then they peed it out. It could be from the pee of an emperor, or from Beethoven or Mozart, or from Napoleon, or from Mao Zedong, or from whoever. Statistically, these water molecules could be from that. And if there is a way to track each one of these molecules, each will have an extremely rich history in the past, from the way it got into the atmosphere to become rain, become snow, become ice, become part of the glacier, and finally fall into here. They have witnessed the entire history. Of course, I'm just talking about famous historical figures, but those are all within a few thousand years. But they could be part of Pangea, the entire Earth continent, as a single piece a few 100 million years ago. It could be part of the Cambrian explosion 350, 450 million years ago. It could be part of the early Earth a few billion years ago, because the Earth was 4.6 billion years old. So put things in perspective. A simple water molecule has a lot of history, a lot of interesting facts about it. But how long will these molecules last? Well, if the Earth continue to heat up, as we know, not only because of global warming, but also because the Earth itself is being heated up by the sun. As the sun gets bigger and bigger, hotter and hotter, eventually it all become vapor in the sky. And if it gets even more hot and hot and hot, it could have so much energy to hit on it. It could become a separation of oxygen and hydrogen atoms. It becomes free oxygen, free atoms in the universe. And eventually, if the theory of the great decay of the universe is true, they will gradually further decay into into energy, become nothing, become stretched out into nothing. And that could happen in billions of years in the future. So in terms of humanity and human species on Earth, all of this is nothing but an instinct in the life of a water molecule. As we know, water molecule could be separated into oxygen and hydrogen by electricity. I forgot the name for it, but basically you put electric node, direct current in it, and it become separation. Well, that was precisely because of the energy you inject into the water molecule that caused the electron to release the bond between the two atoms, because the water as a molecule between oxygen and hydrogen is actually quite stable in the sense that it usually stays as water. Of course, there are a lot of chemical reactions that will make it make the bond break apart, but generally I mean, you can boil the water as hard as you can. You cannot boil it into oxygen and hydrogen. You could even burn it as hard as you can, burn water with vapor. But I don't think you can separate the two atoms. They're pretty tightly bonded. But with electricity, you could do that. And that's one way to generate distilled water. It's one of the purest form of water. Purest form, because there is nothing but distilled water. Well, I take it backward. One of the ways to generate distilled water is to combine oxygen, to burn hydrogen and oxygen, which is the reverse, which release a lot of energy. And that energy after release become pure water. Or you use electricity that creates oxygen and hydrogen, which is the reverse process of distilling water, of generating distilled water. Or I guess distilled water is another way. It's just to boil it into water vapor and let the vapor condense into water. That's actually, I should be corrected. That's how you typically do distilled water. You heat water, boil it into vapor, and let the vapor cool down and condense into pure water. But nothing can be as pure as using what I just mentioned. Hydrogen and oxygen recombined into a water molecule. That is the purest form of water. I guess if I want to do some physics experiment, a chemical experiment, I want to create the purest H2O, I would do it that way. Probably that's what people do anyway. So that's just talking about the water molecule. Of course, the similar history exists for many other compounds. Like these rocks, these are all silicon compounds made from silica, which is one of the most abundant elements on Earth, crust. Because underneath the crust is the iron. But for this is mostly silicon, and they have a long history as well. But on the topic of water, that's what it is.